Welcome everyone. This is separation process course, and today we are going to continue the same topic, which is the multi-stage binary distillation. So we're still talking about multi-stage, where we have more than one stage in a column, and we are still talking about the binary system, where we have only two components, and we are covering the method of separation, which is distillation, which is separation based on the difference in boiling point between a light component and heavy component. Today I'm going to talk about another method that's used for analyzing distillation column, which is called the Ponchon Savarit method. The Ponchon Savarit method. And so far we have discussed the Make-up-Tele method, which is used for analyzing distillation column, even to find the required number of stages or to predict the performance of the column. And as we said that the Make-up-Tele method is basically based on two things: the equilibrium relationships and the material balance. Okay. So today another method called Ponchon Savarit method. This method is introducing another equation that help us in analyzing distillation column, and this equation is related to the energy balance. Okay, so in Ponchon Savarit method, we still use the equilibrium relationship, the material balance, along with the energy balance. The energy balance to analyze the column. So as we introduce a new equation, this means we are going to do more effort. So we are going to reduce the assumptions that we made in analyzing the distillation column. Remember the assumption of the Make-up-Tele method? There was mainly two assumptions. First is that 100% efficiency of plates. That's the first assumption. And the second assumption, of course, this is neglecting any use of any use of sort of efficiency that we discussed last lecture. So we are assuming that we are applying the Make-up-Tele method without any other efficiency, like the mercury vapor efficiency or the mercury liquid efficiency. So basically the Make-up-Tele method was established based on this assumption that we have 100% efficiency of the plates, and the second important assumption is that we have a constant flow rate for each section. Constant flow rate for each section. Okay, so it is like we assume that if we have this is the column and this is the feed and this is the top and bottom products, so we say this is the enriching section and this is the and this is the stripping section, and we say that here we have only one V and only one L. Remember, and we say here we have only one V, we call it V dash, and only one L, we call it L dash, along all the stages for each section. For each section, in each section for all the stages, the flow rate is constant. But in the Ponchon Savarit method, we are going to remove this assumption. So the flow rate will no more be constant, and it will change along each plate, even in the same section. And in order to account to these changes in flow rate, we are going to introduce the energy balance. So this is the benefit from energy balance is to account for the changes in this vapor and liquid flow rate in each section. Okay, so basically the Ponchon Savarit method, it is a graphical method that depends on graphical solution to determine the required number of stages. For example, if you have a design problem and we have a specific XD, so again we have this distillation column and we have one inlet, which is the feed with composition in the feed of the light component, and we have this the condenser. This is the top product, the distillate, and this is the reboiler, and this is the bottom product, and this is the distillate with X distillate, and this is the waste with X waste. Okay, and here there are some stages. Okay, so again we have the same case, but we are going to for example, if we know this, we know this XD, so we know our performance, how to determine the required number of stages using this method, which is the Ponchon Savarit method. Okay, so what we are going to do, the first step for applying this Ponchon Savarit method is, the first thing uh, is to determine the reflux ratio. We need to determine what's the reflux ratio. So for example, if it was given that R is equal 1.5 R minimum, so first we need to determine the R minimum, so then we determine the reflux ratio. So this is the first thing to do, is to determine the reflux ratio. And how we can determine R minimum? You can use makeup delay for determining the R minimum, as we discussed in the previous videos. So you can determine the R minimum using makeup delay method, but and after that determine the actual reflux ratio, and then we can start applying our Ponchon Savarit method. So you can benefit from the makeup delay method to determine this R minimum, and then you can determine the reflux ratio. So this is our first step, is to determine the real reflux ratio, because we are going to use it a lot, this reflux ratio, in the Ponchon Savarit method. So it is a very important parameter. The second thing is that to apply this Ponchon Savarit method, you need to have data. You need to have data. Okay, you need to have data. Data for the liquid phase. Okay, and data for vapor phase. Okay, which is Y. Okay, and for the liquid phase, for different values of X, we need to have a corresponding values of the enthalpy, and we are going to call it H. Okay, so when we say H, this refers to the enthalpy. Small h refers to the enthalpy of the liquid phase. Okay, so we need to have this data, which usually determined experimentally. Okay, so they vary the composition and then measure the enthalpy. Okay, and also we need to have a data for the vapor phase along with its enthalpy, and we are going to call it capital H. So when we say capital H, this means the enthalpy of the vapor phase. So we will have some data and corresponding enthalpy values for vapor. Okay, and these two tables usually determined experimentally. Okay, so this is the first step. We need to have this data, and then the second step is that to draw we need to draw a two-axis graph. So the x-axis will be X, and y. So we can say that this axis represents the composition. One time for the vapor phase and other time for liquid phase. Okay, and then the y-axis will represent what? It will represent the enthalpy. One time for enthalpy for liquid and the other time for enthalpy of vapor. And we are going to use the same axis. So in other words, we will have two lines. One line represent, let me write it again. We will have two lines. Okay, the first line represents H versus Y, the enthalpy in vapor phase versus the vapor composition. The second line will represent the enthalpy in the liquid phase versus X, the composition in the liquid phase. Okay, that's why we are using only a single axis for both composition and a single axis for both enthalpies. But we will have two lines, and each line represents a different thing. One line for H capital versus Y, the second line for H small versus X. Okay, so this is the first step. So this here, the scale will be from 0 to 1 because it's a composition. It is a mole fraction. Okay, and you need to choose a suitable scale for the enthalpy. Usually, sometimes you get the enthalpy in the units that has a high order of magnitude numbers. It is like you see this table, and then you see some numbers like this, 25,000 and etc. So you see big numbers. These numbers usually it is hard to draw in this scale. So what we do usually, so for example, if this is in BTU, British thermal unit per hour, okay, so to simplify the graph you can change the unit. For example, use kilo BTU per hour, so this will be only 25, so you can draw it easily here. Okay, so this is just a suggestion for the scale. You can choose your own scale. Okay, but make sure it has small scale so things become easier with you. So this is the first step. The second step is to draw this data, this H versus Y data and X versus H data. Okay, so we are going to draw them. Suppose they were given, and when you draw them you get this line. So this will be H versus Y, and the other line, let me do it in different color. Okay, so you got, this is another line which is for H small versus X. Okay, and always the enthalpy of the liquid will be below the enthalpy of vapor. Why? Because vapor has a higher enthalpy. Okay, why vapor has a higher enthalpy? Okay, why? Because you need to heat to go to the vapor phase. If you have a substance that's in liquid phase, you need to heat it up in order to go to the vapor phase. And you know from thermodynamics that Q is equal to delta H. So as you heat, the enthalpy will increase. Okay, so that's why always the enthalpy of vapor phase line will be higher than and above the enthalpy of the liquid phase line. So this is the first step for using the Ponchon Savarit method. Okay, now the second step is you need to locate your composition point. See, in this column, so you need to locate your ZF, your XD, and your XW. Okay, so suppose that you have, for example, XD is equal to 0.9, sorry, is equal to 0.9, XW is equal to 0.1, for example, and ZF is equal to 0.5. So you need to locate them in the graph. So we will say here my XW, here my ZF, and here my XW. Okay, so you need to locate where they are. Okay, now the third step is you need to determine what's HD and what is H capital D. So H small, this represents enthalpy of liquid phase. D represent in the distillate. Okay. Similarly, H capital represent enthalpy in the vapor phase. D represent the distillate. So this the enthalpy at the distillate. So this both number will be determined at XD. Okay, because they represent the distillate. So you will search here, we locate our XD here, see, it is here. So you are going to do a vertical line, okay? So this will be your H capital D, and this will be your H small d, okay? These 2 points, okay? This point and this point, okay? So this is H capital D and this is H small d, and you can read them from the scale, okay? So this is the first step. You need to determine your H small d and H capital D, enthalpy in the distillate for the liquid phase and for the vapor phase. After that, let's define a quantity called lambda d. This lambda d, it represents the difference between the enthalpy in the vapor phase minus the enthalpy in the liquid phase, and since we write here d, we refer to the distillate, so we will write here d. So after getting this H small d and H capital D, just get the difference between them and say it is lambda d. Okay, so this is just we are defining a parameter. Okay, but why we are defining this parameter? Because we are going to use it. How we are going to use it? We are going to use it in order to determine the duty of the condenser. What's the duty of the condenser? Okay, so how we can determine this duty of the condenser? Remember from the makeup relay method, we wasn't able to determine the duty of the condenser. Why? Because we neglect the energy balance. Okay, but in the Ponchon Savarit method, they don't neglect the energy balance. That's why we are able to determine the cooler duty, the condenser duty. Okay, so see here there's a condenser, right? And it is removing heat. Okay, so this heat is QC, Q condenser. So how to determine this QC? We need to use energy balance. Okay, so let's take this condenser as our control volume and let's apply the energy balance. Okay, so taking this condenser as my control volume, so this is the condenser. I am just zooming on the condenser, and this is the distillate, and this is the L, and this is the vapor going up from the column into the condenser, and it will condense. So we will have a distillate stream and a liquid going back to the column, which represents the reflux. Okay, and of course, as you know, the reflux ratio will be L over D. Okay. Okay. So first thing, before applying the energy balance, let's apply the overall material balance. The overall material balance will say that V is equal to L plus D. The vapor inlet equal outlet, D plus L, assuming steady state, there is no accumulation. Okay, so this is the first equation. Now, how we can apply energy balance? Okay, let me remove this. Okay, how to apply energy balance? We are going to apply same principle, which is accumulation is equal to inlet minus outlet. Okay, and there is no generation or consumption in energy, so it is only accumulation equal inlet minus outlet. And if we assume steady state, so the accumulation term will be 0, so we can say that the inlet is equal to the outlet, but in terms of energy. Okay, that's it. And to apply this N equal out into energy balance, we can use what we can see all the inlet and outlet energy stream. Okay, the first thing you can see that there is QC, there is a heat removed from the system. Okay, and you can see that each stream, this is stream 1, stream 2, stream 3, each stream has its own enthalpy. Okay, so since this is a vapor, so this stream will have an enthalpy of vapor. Okay, and since this stream, the third stream, is liquid, so it will have an enthalpy of liquid. And since we are talking about the distillate part, so we will call it H capital D and H small d. But what about this distillate? Is it liquid or vapor? Actually, this depends on the type of the condenser. Whether you use a partial condenser or a total condenser. The most commonly one that we use is the total condenser. Okay, as we discussed before. Okay, so first let's discuss the case where we have a total condenser. Total condenser means that this vapor will totally condensate. So the distillate will be always liquid. So we will have here H small because it is liquid and D because it is distillate. Okay. Okay. So this is the first thing. Now let's apply our energy balance. What's the inlet in terms of energy? Actually, we have only how many inlets? Yes, only one inlet, which is H capital D. Okay, and it is entering the system with the flow rate V. So we can say that the first inlet is V H capital D. Okay, and what's the outlet that we have? We have the first outlet is QC. Okay, the second outlet is HD multiplied by D, and another outlet is L multiplied by HD. A question here, is this HD same as this HD? Yeah, they are the same. Why? Because we have here a split point. At the split point, all the intensive properties are same. And since this enthalpy represents joule per kilogram, so it is intensive property independent of the size of the system. That's why we multiply it by the flow rate, which is, for example, kilogram per second. Or in terms of mole, it could be mole per second multiplied by joule per mole. At the end of the day, this is an intensive quantity. Okay, so it will be the same in both sides. Okay, so this is one thing that I want to mention. Now let's continue. Let's continue the solution. Okay, so we have this equation. Let's play with it. I'm going to let QC in one side and moving the other to the other sides. So it will be VHD. uh, minus HD minus HD DHDL. Okay, now let's take a common factor, which is HD. So we will have QC as equal to VHD minus HD, and then we have D plus L. Okay, and we know that from material balance, we know that this V is equal to D plus L, right? From material balance, so we can replace this V with D plus L. So I will have D plus L here and D plus L here. So I can take a common vector and I will say that QC is equal to D plus L multiplied by HD minus HD. Okay. So what's this? What's this quantity? H capital D minus H small d. Remember, we say let this quantity equal lambda d. So we are going to remove this quantity and replace it with lambda d. Okay, so we will have QC is equal to L plus D multiplied by lambda D. Now let's divide the both sides. Let's divide both sides by D. So we will have QC by D as equal to L over D. What's this? L over D. Isn't it R? Yeah, it is R, the reflux ratio. So we can replace it with R, the reflux ratio. And D over D is 1. So this is our final equation. So if we know lambda D from the graph, and we know the reflux ratio from the minimum reflux ratio, and we know the distillate from the material balance, we can determine the condenser duty. Okay, we can determine the condenser duty. But be careful, please. This is assuming total condenser. This is assuming total condenser. What about if we have partial condenser? So let's draw it again. So we have here, this is vapor, this is distillate, and this is liquid. And so here HD and here H capital D. If we have partial condenser, so here I'm talking about partial condenser, so I am going to return the liquid back to the column. Okay, so my product will be vapor. In other words, it will be H capital D because it is vapor here. Okay, so let's do the energy balance again in equal out in terms of energy, and we have here QC. Okay. So we have only one inlet, which is VHD, and we have the first inlet, LHD. This is the second inlet, plus DH capital D, and we have this QC as outlet. Sorry, they are all outlet. This is the inlet, and they are all outlet. Okay. So this will be plus QC. Okay. Now again, replace this V with L plus D, because inlet equal outlet in terms of mass or material balance, mass or mole. Okay, so we will have L plus DHD is equal to QC plus DH capital D plus LH small d. Okay, so we can distribute this H capital D, so we will have H capital D plus H capital D will be equal this. Okay, so you can see we have on this side we have dH capital D, and we have on the other side dH capital D, so they can cancel each other. Okay, so we will end up with QC. This QC is equal to this LH capital D, okay, minus, because I take this to the other side, minus LH small d. I can take a common factor. Let me write it on the next page. I can take a common factor L, so I will have H capital D minus H small d. And what's this? Again, what's this? This is lambda d. Okay, so I can divide both sides by d. L over d, what's this? This is the reflux ratio. So I will end up with QC over d is equal to R lambda d. Okay, so you can see the difference. For partial condenser, if I know lambda d, which is H capital D minus H small d, and I know the reflux ratio, and I know the d, the molar flow rate of the distillate, I can determine the condenser duty. So this equation is for partial condenser. This is for partial condenser. And you can see the difference here. For partial condenser, QC over D is equal to lambda D multiplied by R. But for the total condenser, this is for the total condenser, QC over D R plus 1 multiplied by lambda D. So we have here plus 1, which is different here. Okay, so we finish with the energy balance equations. Now let's define a point in this graph. See this graph, the graph that we have this graph. Let's define a point called OD. This point OD, is called the top section operating point. Okay, the top section operating point. Remember, distillation column, we have the top section and the bottom section. So this point is called the top section operating point. And this point has a coordinate. You know that any coordinate for a two-dimensional plot will have only two sets, right? One for the x-axis and one for the y-axis. Okay, so for the x-axis, this will be xd, and for the y-axis, this will be h small d plus qc over d. Okay, so if we know our performance xd and we determine hd small from h small d from the graph, and we determine qc over d using either this equation for partial condenser or this equation for total condenser, we can determine OD on the graph, right? So we will have, this is for y-axis and this is for the x-axis, and we can go here to the graph and determine this point. So for example, if it is here, this will be my OD, the black point. Okay, you can read it from the x-axis and the y-axis as these values that you get. But the question here, how we are going to benefit from this point, we will see how we are going to benefit from it in the next lecture. Okay, now one last thing that I would like to mention here is that you need also to determine the enthalpy of the feed. Okay, we need to determine the enthalpy of the feed, and we are going to put a bar here. So this bar represents the average enthalpy of the feed. Okay, So why we are saying it is average enthalpy and how we can determine this enthalpy of the feed. This enthalpy of the feed can be determined. We have three cases mainly for the feed. It is either Q equal 1, saturated liquid, or Q equals 0, which is saturated vapor, or Q between 0 and 1, which is saturated mixture. Okay, so for the first case, where Q equal 1 saturated liquid, how we can determine this H feed? So simply, remember I said that you need to determine the feed composition, ZF, so we can go and draw a vertical line and see here, the intersection with H small line, this will be the H of the feed if we have saturated liquid. If we have saturated vapor, so it will be the intersection with the H capital line. This will be my H feed. If I have saturated mixture, my point will be somewhere here, in this rectangle, or in this line. Okay, so if I have saturated liquid, it will be down. If I have saturated vapor, it will be up. If I have saturated mixture feed, it will be in between. So how I can determine the place exactly of my feed point if I have saturated mixture? Simply I need to determine the H in the vapor phase and the H in the liquid phase for the feed. So let me call them at ZF. If I have saturated mixture, this case Q between 0 and 1. Okay, so I'm going to get H small f for the liquid phase and H capital F for the vapor phase, but both at feed, that's why I'm referring to them as F. Okay, then I will say that the enthalpy of the feed average, that's why we put bar here, is equal to Q, the percentage of liquid, multiplied by H small f, plus 1 minus Q, the percentage of vapor, multiplied by H capital F. So using this, I can determine my HF exactly. So I can say where my HF exactly here, where it is. Is it here? Is it here? Is it here? I can use this equation to determine its place exactly. Okay. Now in the second lecture, or in the next lecture, I'm going to explain exactly how we can proceed and apply this Ponchon Savarit method in order to determine the required number of stages. And thank you for your listening. I wish you all the best.